Hi everyone. So last time we started chapter 10 and we started the heat equation and we were trying to solve the heat equation. And finally we came up with an equation where we need to express the initial temperature distribution as a series in terms of sines. Okay? And today we will learn actually how to express a function, of course if available, maybe it's not true for every function, in terms of sines, also cosines. But before that, as I promised, I wanted to talk about last time boundary value problems, but I left it to this lecture. So today I will start, before we come up with this sine and cosine series, I want to talk about the boundary value problems and their nature. We will not get into too much details. I just want to give you the following feeling. I mean, their nature is quite different than the initial value problems. So what do we do in the boundary value problem? So let me just give you a brief and very simple example. Think about a second order differential equation which has constant coefficient. Okay. And let's say you have a boundary value problem. So I need to tell you what's happening on the boundary. So let's say that yt0 is y0 and yt1 is equal to y1. So here I'm assuming t1 is bigger than t0. So what is this problem telling me? So I'm giving you two values, t0, y0, and t1, y1. Okay. So basically, I give you 2 points. So I'm looking for a function, basically, which will pass through this point and this point. And in the middle, it must satisfy the given differential equation. All right? So basically, here your domain, you can think like between t0 and t1. So on the boundary, I'm specifying the values. And then I'm leaving the mid part here, the interval, the open interval. How will I fill? Of course, according to the given differential equation. So there needs to be a curve, whose graph, let's say, a curve whose graph passes through these points. And so if you think about this function, y, the curve is the graph of that function, which satisfies this differential equation. Okay? So basically, this is what the boundary value problem says here. Of course, I mean here, I gave you boundary of an interval. If you try to do like maybe a two-dimensional domain, and your boundary will be a curve, so you have to fill inside, like the heat equation. So we gave you the problem basically on a strip. So we gave the initial condition. Eventually, if you look at the domain, it becomes a boundary condition too. And we were trying to fill inside. So here, this is the boundary. So you have to fill inside according to the differential equation. Their nature is different. So if you remember for the initial value problem, so if you think about the same differential equation, I need to give you, again, like this one, two values, but they are given at the same point. So you can think one of them is the initial position, and the other is its like initial velocity. So here you give t0, y0, okay? So you say, yeah, it's going to pass through this one with this derivative. So like you are giving a slope there or direction there. So let's say it's like this direction. So then you should find the curve passing through this point with this direction and satisfying the given differential equation. So basically, on a neighborhood, on an interval around t0, you need to find a curve satisfying these conditions. So here, so this will be defined depending on, of course, the problem. There may be a larger interval or a smaller interval. Okay, so here it's obvious, I mean, because it's constant coefficient, but it could be worse than this. So their nature is at this, from this, I give you two conditions, but at different points. Here, I give you these two conditions at the same point. Okay, now, what I want to do is the following. I will give an example to teach you something about their nature. It will be a very simple example, but on this example, you will be able to observe that, I mean, their nature is quite different. Even like, I mean, if you remember, for the linear equations, by just looking at the coefficient functions, you could say something about the solution's domain. And you can say, the solution exists. Yeah, it's unique, this kind of things. But for boundary value problems, it's not quite obvious. All right, so I will take the same differential equation for all examples. So my differential equation is the following. Okay, my differential equation is the following equation. And for the first example, okay, my boundary condition is y0 is 1 and y of pi is equal to 5. Okay, now let's look at this and let's try to solve this. Okay, so if you look at this one, I can easily solve this because its characteristic equation is lambda square or r square, whatever you pick, equal to 0 plus 1. So from this, lambda is equal to plus minus I, and so I get the following general solution. C1 cosine t plus C2 sine t. So now this is the general solution. I want to satisfy these conditions. So when I plug in 0, I must get 1. So if I plug in 0 here, cosine 0 is 1 and sine 0 is 0. So this is what I get. And second, when I plug in pi, I need to get 5. If you plug in pi here, cosine pi is minus 1. We have minus C1. And sine pi is 0. So this is what we get. So what does this thing say now? It says that C1 has to be 1. But this thing says that no, C1 has to be minus 5. So there is no number which will satisfy both these conditions. So automatically you understand that, I mean, there is no solution to this problem because we know the general family and no member of this family will satisfy these conditions. So for this thing, now we see that no solution exists. Okay. Now let me fit another example here. The same differential equation, but my conditions are different. So this time I'm taking y0 again 1 and y 3 pi over 2 equal to minus 1. Okay. So this time, if you plug in y0 is equal to 1, same, so we get C1 and minus 1. So we have y of 3 pi over 2. Okay, so if you plug in 3 pi over 2, cosine 3 pi over 2 is 0. And sine 3 pi over 2 is minus 1. So we get minus C2. So this thing says that C1 has to be 1, C2 has to be 1. And so we get the following solution. Y of t is equal to cosine t plus sine t. So what did we get? We get a unique solution. Solution here. Okay. Okay, now the final thing, right? Okay, y0 is 1, y pi is -1. So I didn't change the differential equation, if you notice. I'm just changing the boundary conditions. So if you look at y0 is 1, which says that C1 has to be 1, and y pi has to be -1. If you plug in pi, cosine pi is -1, so we have minus C1, and sine pi is 0, so this is what we get. And from this, we just get the following. C1 has to be 1. That's the only thing. So then what is the solution? So the solution is we have cosine t plus C2 sine t. So for any C2, it is satisfied. So as a result, we see that there are infinitely many solutions. So infinitely many solutions. Okay. So now I didn't change the problem at all. Okay. Even, I mean, if you look at in these example, I fixed one of the points. So, but as you see, like we got 3 possibilities. So if you remember, for the initial value, basically if you look at the coefficient functions, initial value problem, you look at the coefficient functions, somehow if they are nice around the given point, then nice means like continuous around the given point. So then we were able to get a solution, and most of the time it was unique. But here, our equation is very simple. If you look at its coefficients, they are constants, they are continuous everywhere. But I'm changing my boundary conditions, I'm getting all possibilities. Even I'm fixing the first one, I'm changing just the second one, I'm getting all possibilities. So that's the reason somehow it's not like the initial value problems. Your control is not quite obvious here on the problem. You may have all these things. Okay? All right. I hope I gave you this feeling. I mean, their nature is quite different, so you have to solve it, and then you'll see. It's not easy to say beforehand, just looking at the coefficients. All right. Now, let's go back to our problem. We were trying to express our function in terms of sines. Also now we will do generally in terms of sines and cosines. So what is the name of this thing called? It's called Fourier series. Okay. So probably this is 10.2. So I started from 10.5. Heat equation, we got stuck. Now we are coming back. So, Fourier series. What's a Fourier series? Right? So, definition. A series of the form A0 over 2 plus n from 1 to infinity, an cosine n pi over L x plus bn sine n pi L x is called a Fourier series. Called a Fourier series. So you can think it's an expansion in terms of sines and cosines. Actually, I mean, you see like A0 over 2. Why? I mean, it's constant. Actually, there's a cosine here, which is cosine 0 pi over L. Okay, so cosine 0 is 1. That's the reason here we have 1, and that 1 is actually cosine. Okay, so a series of this form is called Fourier series. So expansion in terms of cosines and sines. All right. Now, remember our problem was to express a function in terms of this. So then you come up with the following question. Which functions can be expressed this way? That's the first question. And if I can express, then how will I find these things, ANs and BNs? How will I compute these things? Now we will come to that one. But before this, suppose that a function, has such kind of expression. And what can you say about this function? So by using equality, you should be able to say something about the function. Okay? Now, I just want to pass the following quickly. Of course, this is a general Fourier series. It's a general Fourier series. It contains then sines and cosines. If there are no sines, if you just have cosines, it's called a cosine series. Okay? So, let me just write it here. If AN, let me just start with the AN maybe. If ANs are all 0 and bigger or equal to 0, it is called a sine series. If all BNs are equal to 0, it's called a cosine series. Remember, in the solution of the heat equation, basically we for the homogeneity of the heat equation we did, and we were trying to get a sine series. There wasn't any cosine there. Okay. Now, let's try to understand this. Which functions can be expressed? So, suppose a function has such an expression. Suppose f of x is equal to a Fourier series. What is the first thing you can say? So if you look at, this inequality, and if you look at this right-hand side, I see cosine and sines. What is the first thing you say about these functions? They are bounded. Oh, okay, great. But yes, they are bounded, but their coefficients may be large. The second thing maybe we know about these functions is these are periodic functions. So all of them are periodic functions. So what is the period of cosine and pi over L? So we know that period of cosine and pi L, and also similarly for sine and pi Lx is equal to, we know the usual period, like if it were 1, it was 2 pi. So if you divide by this number, which will be basically the frequency, and then you get the period of these things. So if you divide by n pi over L, so pi's are cancelled. When you flip, you get 2L over n. So all of them are periodic. Each now, if you look at these, then just these two, one, but n is changing here, not if you notice. And it's changing, but when n changes, you are getting different periods. So their periods are getting smaller and smaller. But all of them actually have a common period, which is 2L. So, I mean, you are chopping your periods. You are just getting smaller, maybe, periods for as n gets larger and larger. But still, all of them, for every n here, if you shift 2L amount, then the result doesn't change. So that means all of them have a common period, which is 2L. I mean, each has a period 2L and over n, but there's a common period. There's a big number which I can use a period for all of them, and that number is 2L here. So then, if this is the case, the common period, so then 2L is a common period for all. So which says that if 2L is a common period, so then this function f of x must be a periodic function. And what is the period? So its period must be 2L. So we understand this. Not every function can be written this way. It must be a periodic function. Here, if you have this expansion, then its period must be 2L. So now we get this conclusion. We will be interested in periodic functions. How about the other things? Will it be a continuous function, smooth functions, more analytic functions? We will answer that question. Actually, we will borrow a strong theorem, and which is called Fourier Convergence theorem later. That will answer. But before that, now, okay, we got this. Suppose we have an expansion. We understood your function must be periodic. So now the second question, suppose you have an expansion. How are you going to compute these things? ANs and BNs. What is a formula? And here, we will use some knowledge. Maybe you've seen this thing in calculus course, so in linear algebra courses. Basically, we will use some nice properties of these cosines and sines. So remember, in calculus courses, we taught you something about dot product. And dot product basically determines the geometry in the Euclidean geometry in Rn. So when you were given a vector, let's say a V, and let's say W, and if this is equal to, in terms of coordinates, V1, Vn, and here I'm drawing something in n-dimensional space. Of course, it's two-dimensional, but if you have this, and if you have these coordinates, and their dot product, V dot W, is equal to V1 times W1 plus until Vn times Wn. This was the thing we taught. Okay. And by using this, we talked about whether two vectors are orthogonal to each other or perpendicular to each other. If the dot product were 0, then we say that these things are orthogonal. So if this is 0, then they are orthogonal to each other. Okay, this was the thing. Okay. And so by using these, and we talked about their length. So the length of a vector or magnitude of a vector, norm of a vector was defined. You take a dot product with itself, and you take the square root. This was what we had. So this thing says that v dot v must be bigger or equal to 0. It is 0 only when v is the 0 vector. This is what we know. And finally, we talked about projection. How to project one vector over another vector. And also this was done by using the dot product here. Okay? And so we talked about projection. Okay. So you project v in the direction of w. So this w determines a direction here, and you project onto this. Okay. So this big one is your projection. You write this is projection of v onto w. So basically you find the component of v in the direction of w. And how do you find it? So first of all, since it's in the direction of w, it must be a multiple of w, because any vector in the direction of w must be a number times w. What is that number or scalar? And this was done by dot product. So we take v dot w. You can check this formula from calculus books. And divide by norm square of the w vector. So this way we were able to compute the projection onto this. And this also we use this projections. So use these projections actually in physics courses. I mean, if you remember. So remember, like when you were given a vector, let's say in physics courses, typically, I mean, we write them like by using I, J, and K. What is special about this I, J, K, and they are orthogonal. They dot product if you pick 2, and you get 0. Furthermore, I dot I is 1, J dot J is 1, K dot K is 1. So their norm is 1. So basically you get orthogonal set of vectors when you say take I, J, K, and also they are unit vectors. And if you want to find this A, which is the component of V in the direction I, then what you do, you take the V vector, dot product with I, divide by the norm square of I. So, for example, A here is equal to, from this formula, V dot product with I, and I norm square. But I norm square, I has norm 1, so this is exactly equal to V dot I. So this way, basically, I mean, when you do the projection, you are finding the components of V in these directions. So when you add them up, then you get V back. So I give you this component, when you add them up, you get the V back. Okay, so this was the idea. So what is the relation here? Here, actually, we are going to use the same thing for the cosines and sines. So these cosines and sines replace the same thing as like here. They will do the same job as I, J, K. So they will be orthogonal. But they are functions, not vectors. So what do you understand from vectors? I mean, of course, you don't understand. When you say vector, it has a direction. It's like this. No. In terms of mathematics, like if you think about vector space, you have some elements, and you can add them. You can multiply them with scalars, so you can just change their length, if you think. So for the functions, I can add them. Like the vectors here, I can add them. I can multiply a function with a scalar, so I could do the same things. So I can consider the functions also as vectors here. Okay, you have a dot product here. It's quite natural. I mean, you just multiply the components, the corresponding coordinates, and you add them up. What are you going to do for the functions? What kind of dot product you are going to define? So when I'm going to define something, it must have similar properties as here. What are those things? So when you take dot product of two vectors, you get a number, scalar. Okay, so if you have some linear property, so if you have V plus U dot W, so you can distribute, and this kind of things. So, and furthermore, if you take V dot V, it must be bigger or equal to 0. So then when I define something, it must have this property, like norm of a function must be bigger or equal to 0. So now we define the following inner product, or dot product, you can think. Okay. And actually, you can do this thing more generally, but since I'm working with these cosines and sines, and like as I learned, I will need some periodic functions, I will just work on functions which are 2L periodic. Okay. So let F and G be 2L periodic functions. I'm assuming that, I mean, these are integrable functions. So most of the time they will be piecewise continuous functions. So I can integrate. Okay. So, and I'm defining the following. F, G, like F dot G you can think. The integral from minus L to L, F of X, G of X, you can think like, or F times G dx. Or, which is the same thing also, the integral from 0 to 2L this. First of all, why it doesn't matter? Because these are 2L periodic. So if you take a 2L length interval, then if you know the functions there, you know the functions everywhere. So I'm just integrating over one period. Either you integrate from minus L to L, or from 0 to 2L, or from 2L to 4L, or L to 3L, whatever you take. So this integral won't change. So talking about 2L periodic functions, like since I'm doing integral, so you can think like these are integrable functions, and most of the time we are going to work with piecewise continuous functions, which are integrable over these domains. So I'm defining such a thing. So you can easily see like the following things. if I write here f plus h, comma, g, so here f plus h, so f times g, h times g, so they are added, so you can easily get this linear property. If there is a constant here, c times f, you can take c out. You can take it out, so linearity. And furthermore, we have v dot w is the same as w dot v, so symmetry. Okay, here again, if you switch them, nothing changes because f times g is the same as g times f. And last thing, when you have v dot v, it's always bigger or equal to 0. So if you take the same function f, so you get here f square is always bigger or equal to 0. So their integral will be bigger or equal to 0. So this is what we get. And if you think just continuous functions, you have the 0 only when f is completely 0, like the vector is 0 case. All right, so I defined such a thing, so which has similar properties to the dot product. Now, I want to prove the following. If I take cosine and pi l x, sine and pi l x, if you take this set from 0 to infinity, let me do this way, because if I write here 0, it becomes completely 0. I cannot include 0. Let me just take 1. And also, let me include 1 here. All right. Maybe so it's the same thing, but let me use 2 index. All right, or whatever. It's better. So here, n is from 0 to infinity, and m is from 1 to infinity. That's better. So you have all sines and cosines in this form. N is from 0 to infinity, so you have 1 there, and m is from 1 to infinity. So you have a huge set. Now, I'm claiming that this set is an orthogonal set. Orthogonal set. With respect to this product. Okay? This inner product, or dot product, if you say. So then what do I need to prove? I need to prove that if I pick 2 different members, they are orthogonal to each other. So I have to show that cosines are orthogonal to sines. Sine is orthogonal to sine if the index in sides are different. Okay. Similarly, cosines are orthogonal to cosines if their insides are different. So let's start with cosines and sines. First, if I take cosine and pi Lx, sine m pi, this is equal to, from minus L to L integration, cosine dx. This is what we have. So, but if you look at, we know that cosine is an even function. Sine is an odd function. When you have an even and odd function multiplied, the result is an odd function. So you have an odd function on a symmetric domain from minus L to L, and we know that this integral has to be 0. So cosines are perpendicular to sines. How about cosines and cosines, sines and sines? So let's take, I will do one of them. Let me just do cosine. Sine version is also similar. Cosine n pi L x and cosine, let's say m pi Lx. So I'm just saying I'm taking two different ones. Okay. Minus L to L. Cosine yes. Okay. So we have a cosine times cosine. So I never remember this formula, so I will copy this one. So what is this equal to? So we have the sum of the insides and difference of the insides and written as cosine and cosine, and divided by 2. So this is equal to 1 over 2t from minus L to L cosine n plus m pi over Lx plus cosine n minus m pi Lx dx. This is what we have. Okay. Yes. All right. Now, after this, what do we get? So if n and m are positive things, the only problem may occur when this is 0, because I know the antiderivative of cosine kx. What is the antiderivative of cosine kx? That is sine kx divided by k. So here, if I integrate these things, 1 over 2, antiderivative will be sine n plus m pi Lx divided by n plus m pi L. And similarly, this one, sine n minus m pi Lx divided by n minus m pi L minus L to L. Actually, I could do better. Like, I mean, these are even functions, so I could integrate from 0 to L and double it, but we will see. Nothing changes. So this is what I get. There's only one problem here. Since n and m are positive, there is nothing wrong here, but if n and m are positive, if they are same, then this formula doesn't work. So since I took at the beginning, different members, I'm not taking the same member, I'm taking a different member, so this formula is fine. So here n and m are not equal. N is not equal to m. So then, what do we get? If you plug in L or minus L, L here, L, so you get a cancellation, you get a multiple of pi. At multiples of pi, integer multiples of pi, sine is 0. This is also at multiples of pi, sine is 0. So all these things are 0. If you plug in minus L, nothing will change. You will get another multiple of pi, so you get 0. So we get 0. So cosines are perpendicular to cosines if you pick two different members. How about, okay, so now we did the proof. There's only, you need to do the same calculation for sine and sine, and again, use a similar formula, and you get a similar calculation, and eventually you will see that sines are perpendicular to sines. So we now get the proof that, of that it's an orthogonal set. So if you pick two different members, they are orthogonal to each other. Only as an exercise, you can practice the two different members of sines. Okay? So it's orthogonal set. Now, I also wonder one thing, because since I will do at some point projection idea, and how about if I take them same? Which means like if I pick same member, and then we know that if you pick the same member, you are going to compute the magnitude, the norm, the length of the given function square. Square of the norm. So now let's try to compute that. So I will need it. So if these are both n, then what do I get? This is the good part about using the board. Okay, so so then we have this. Okay. Now, from minus L to L, cosine square. So we will use double angle formula. So what are we going to get here? We will get the following. Now, remember, 2 cosine square theta minus, so let me maybe start from here. So we know that cosine square minus sine square theta is equal to cosine 2 theta. So in the place of sine square, if I write 1 minus cosine square, then I will get cosine square minus 1 minus, so the minus makes it plus, so we get 2 cosine square theta minus 1 is equal to cosine 2 theta. So if you take 1 to the other side and divide everything by 2, we get the expression of cosine square in terms of this. So it says that, so double this, and we have now cosine 2 n pi divided by Lx plus 1 divided by 2 dx. So if you look at the integral of this, we have 1 over 2, we have sine 2 n pi over Lx divided by 2 n pi L, and 1 over 2 x from minus L to L. So similarly, if I plug in L here, I get a multiple of pi, so which means I will not get anything here. It will be 0. For minus L, it's true. So this part will not contribute anything. If I put L here, I get L over 2. If I put minus L, I get minus L over 2. If I subtract them, then I get L. L over 2 minus L over 2, I get L. So this is what I get. But there is one thing we are forgetting here. This formula is fine whenever n is not 0. But for the cosine, we have n equal to 0 case too. So here, I'm assuming n is not 0. Because if n is 0, we get 1, 1. So let's do that differently. If you have 1, 1, which means cosine 0 pi over L x. So this time, 1 times 1 dx. So we have x from minus L to L. So this is going to be 2L. So among all these things, among cosines other than 0, they have norm square L, but 1 tells us norm square of this 1 is 2L. So that's one difference. So you can do the same calculation for sine. So you will see the same thing for sine. So you will see the same calculation for sine. But there is no sine 0 because it's already 0. So if you do sine and sine, if you do the sine and sine, sine n pi x, sine n pi L x. So if n and m are different, you are going to get 0 because it's an orthogonal set as we said. If n is equal to m, then again, like we did for the cosine, we will get L. Okay, so this is what we get. So now we proved that it's an orthogonal set. Furthermore, we said something about the norm of the components. Okay. All right. Now let's go back to our business. We want to express a function in terms of sines and cosines. And now, somehow, this function must be periodic. And so, we show that actually we have such a nice set of functions, which are cosines and sines, which are orthogonal. And now, I want to express my function as a series of sines and cosines. How am I going to do this? The idea is very simple. Okay? Now, let me first of all start that with the assumption, because I'm using this. Suppose I have a Fourier series. Suppose my function has a Fourier series, so I'm using it. So suppose f of x has the following Fourier series. Okay. Now, from the observation, this function must be periodic. Furthermore, all these members form a set which is orthogonal. Okay. Now, I want to compute ANs and BNs. But actually, now it is obvious because remember, V A I B J and C K. So you want to express your vector in terms of I, J, K. What is special about I, J, K? They are orthogonal. So you are decomposing your vectors in terms of I, J, K. So you are finding their components. And then when you add them up, you get V back. Okay? So if you do like two-dimensional version, just to show you, if V is a vector in 2 dimension, so what you are doing is the following. This is your V vector. You are finding its component in the I direction. You are finding its component in the J direction. Okay? So this is the I direction. This is the J direction. Okay, so basically this vector is exactly A times I, and this vector is exactly B times J. When you add them up, you get the V back. So you are decomposing into parts, the components. So now, It's a similar idea here. I'm decomposing my function into parts. But when I add them back, I get f back. So I'm starting with this assumption. I'm saying, yes, I can write f in terms of this. So you are writing this way, like ij, just two elements, orthogonal. Here I have tons of elements, so I have an infinite member here. So I'm decomposing it into those components. So how did I find A here? I took the projection of V onto I. So if I want to find AN, I need to project F onto this direction. If I want to find Bn, I need to take projection of this into this direction. So if I want to find what is A0, I need to take the component, I need to find the projection of F in the one direction, cosine 0 direction. So this automatically tells me the following. An is the coefficient in the cosine and pi over Lx direction. So then, if you want to find An, then you need to take the product, dot product in the cosine with f with the cosine and pi Lx, and divide by norm square of this, cosine and pi Lx. So what is norm square? Norm square means cosine dot with cosine. But we already computed that one. And that is 2, that's L. This was L. So this formula is then 1 over L times, so what is this thing? This is just an integral from minus L to L, from minus L to L, f of x times cosine and pi Lx dx. Okay, but only one thing. For when n is 0, this number changes. Because when n is 0, you get 1 norm square according to this. I will come to that one. Okay. So this is what we have. Similarly, for Bn, so now you have to take the projection into the cosine direction. So we have f of x sine and pi over Lx divided by sine and pi Lx norm square. But again, this was L, so we get the following formula: 1 over L minus L to L, f of x sine and pi over Lx dx, right? So now we got Bn. How about if I do the same thing? Now there is only one thing left when n is 0 for cosine. So this formula is true when n is bigger or equal to 1, n is bigger or equal to 1. How about n equal to 0 for cosine? This time, we get cosine 0 is 1. So I need to take norm square of 1. But norm square of 1 is 1 over 2L 1 over 2L from minus L to L, because it's now 2L, and we have f of x dx, because I'm multiplying with 1. Formula changes. But remember now, in the formulation, we have here a0 over 2. Basically, what I'm doing, I am doing the following. I'm taking the projection of f of x not in 1, I'm taking in 1 over 2 direction. So that I get here a0. So if you replace here not 1, but 1 over 2, this is 1 over 2. Okay? And this is 1 over 2 here. So you get 1 over 4. So you get basically just, if you do L. So what this thing says is the following. Actually, if I think that way, over 2, so I'm projecting over 1 over 2 direction, that automatically gives me this for computation, not this computation, but the following computation. If I just take this computation, now if I take this, I'm not going to compute. So if I do this computation, then this automatically gives me a0. That's why I'm writing here a0 over 2. So here you have 1 over 2 basically in your computation. So that's somehow arranged here if you use a0 over 2 in your formulation, like taking projection onto the 1 over 2 direction. And so this way you can just combine that formula with this formula. And that's why in the book, in this book, it's written a0 over 2, so you can use the same formula for all of them. So now I'm erasing this and telling you, yes, you can use the same formula for all as long as you write here a0 over 2, not a0. Because if you are not going to use this, like the other books, they write a0 here, then for a0 you have to use the 1 over 2L formula, not 1 over L formula. But if you want to use the same formula for all cosines, like the book does, I'm writing a0 over 2, and we are using this formula for all of them. But when n is 0, we are basically integrating from minus L to L, dividing by L. But in the Fourier series, we are writing a0 over 2. Okay, that's what we have. All right. Now, these are called Fourier formulas, which allows us to compute the coefficients. Now, I want to finish. So at least, partially we learned something about Fourier series. And we have a feeling that, we must work with periodic functions so that we can find their Fourier series, but still don't know. Maybe we need some more conditions. And we know how to compute their coefficients by using these Fourier formulas, we call them. Or Euler Fourier formulas are, you can give the other names also. And at least maybe you can say the following. So since the computation involves something about just integration, as long as, I mean, your functions are integrable somehow, it may be fine. But next time we will start with the Fourier convergence theorem, which will actually tell us when we will have Fourier series. Here we did all these computations under the assumption that we have a Fourier series. And if you have a Fourier series, then it says that by these formulas we can compute the coefficients. So for which functions, at least we must have the condition, f must be a periodic function, 2L periodic function. So next time we will start with the Fourier convergence theorem, which says that which functions under these assumptions definitely you have the Fourier series, and by using these formulas you can compute the coefficients. And then we will do some examples of Fourier series. And then we will do some cosine series, sine series. Eventually, I mean, we will learn how to find the complete solution for the heat equation. All right, see you next time. So this video is recorded on 31st of December. So I wish all of you, to the world, a better year. So hopefully in 2021 we will have a better year in terms of our health, in terms of success and other things. So I don't want to say this, but I want to make this bad joke. See you next year.